there to be a difference between branch coverage and condition coverage and multi-condition coverage and so forth. Now, in terms of loop coverage, notice that we would have to test with n equal exactly 1 in order to test that. Since that's a greater than 0 value, then we could use that instead of, say, 2. And n equals some maximum. And then the maximum is going to be determined for this particular program by either a requirements specification, ideally, what's the maximum length Fibonacci series that this thing can generate, or in default of that, it will be determined by the point at which the integer values overflow. And for one of those, at some point or another, that integer variable c will overflow, and that will stop the program. Of course, it's extremely bad programming practice to rely on some sort of internal mathematical overflow error to terminate the program. So that, I would say, that is definitely a bug. So in the absence of any stated maximum, then one should test this all the way up into the point where it does overflow, and then you would file a bug against that. Okay, so let's take a look at condition coverage a little bit more closely here, just to try to clarify the point I was making a moment ago. Get my highlighter going here. So if we look at lines 1 through 5 here, these guys, if we say condition coverage, we want condition coverage, then we have to have true, false, and true and false. Right, now notice that conceivably, this could be done with just 2 tests. You could have true, true, and you could have false, false, all right? Which is, of course, exactly the same as what you would need for branch coverage or decision coverage here. Multi-condition coverage, then it would be, as I said before, true, 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 false, false, true, false, false. So we've got 4 tests. And then multi-condition decision coverage, it's true, 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 false, and false, don't care. They can be either true or false, so there's 3 tests. Okay, now let's look instead at lines 7 through 11, because this is an interesting possibility here. Now notice here, we're checking to see if this value f is not null. And then we're checking to see what it points at. Okay, so apparently f is a pointer, and we're checking to see if the value that it's pointing at is 0. Now, notice that if this first condition is false, in other words, it is null, then this second condition here is meaningless, and in fact, it would be a bug to try to execute it, right? So, of course, given the way that this is defined, it should not try to execute it, right? It should, the compiler should say, okay, well, that's not going to happen, and so I don't need to try that. So, with this one, again, you've got true, you test true, true, and then false, but that if you test that with false, then this can't be any value one way or the other, right? Because it's nonsensical to ask what a null pointer is pointing at. So in order to get condition coverage, you'd actually have to test true and false, right? And then true, and then false, and don't care. So that would actually, in that case, multi-condition decision coverage and condition coverage would be the same thing, and multi-condition coverage would result in a meaningless test. You couldn't actually achieve it because we couldn't have false and true, or false and false for that matter, because again, this condition is undefined in the case that the pointer is null. And lastly here, let me clear this out. We look at 13 through 17, right? And now, so this is an OR. So you notice that this is the logical backward or logical opposite situation of the lines 1 through 5. So if the A less than or equal to 0 clause evaluates to true, then we don't have to go on to evaluate this because the overall compound condition will evaluate to true. So condition coverage would be the same thing. You know, it'd be true, false, and true, false. Now, in order to check that, remember that in order to actually get this to evaluate in a compiler, you'd have to make sure that the execution flowed there, right? So this would have to be false in order for this check to happen, which is the opposite of what would happen here. This would have to be true for this check to happen. So we would have to get, we have to say false, true, and then true, false in order to get condition coverage. Now, for multi-condition coverage again will be the same as before. It's the true, 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 false, false, true, false, false. In this case, we can actually do that, which was not true up here because of this condition here. And in the case of multi-condition decision coverage, it's true and don't care, and then false, true, and false, false, the things that we need to look at there. So as you can see, that can get a little bit hairy, and just explaining it can be a little bit challenging, and then so you can imagine trying to figure it out, tracing through a program. So it's good to have tools to do this, but you do need to understand that, you know, as I said, things like multi-condition coverage in some cases can be impossible, like in the situation in lines 7 through 11 on this slide. Okay, now, McCabe's cyclomatic complexity. This is something that you might run into if you are looking around at tools. There are tools to support this. And basically what Tom McCabe was trying to do, and I saw that somebody sent the paper, and I'll mention the link when we go through the Q&A. You'll see this if you read his paper. Basically what McCabe was trying to do in his research on this was to figure out why it's so hard to write programs without bugs in them. And what he stumbled on was this realization that you can look at the amount of branching in the program as a surrogate metric for its complexity. Now, by surrogate metric, what I mean is the thing that you can measure directly, which tells you a lot about something that is very difficult or perhaps impossible to measure. Now, there are many different ways that we could try to measure the complexity of the program, and some of them get pretty tough to measure, like, for example, Halstead's complexity measure, which you can find discussed in Beiser's book, Software Test Techniques. And that's a real challenge to try to get your head around what that means. McCabe said, well, let's make this simple, that programs are complex because there's branching, where there are situations where one of two things is going to happen, or one of n things is going to happen in the case of a switch case. And since that's the situation, as you write the program, you have to keep straight in your head the possibility that there are multiple things that can happen. And that information is something that has to get stored. And there's psychologically, there's some work that's been done on this. And it's not just psychological, it's actually, you know, brain science. There's a part of your brain that holds the working memory, the short-term working memory, and it is very limited in its capacity.